Hi everyone, welcome to the second experiment of engineering visualization. The sessions being organized by Department of Electrical Engineering. Our first experiment was on circuit visualization and our second experiment is on frequency visualization. So by frequency visualization, we mean that we will be viewing the frequency content of various types of audio signals. Okay? So before we move to audio signals, what do we mean by frequency content, right? Suppose there's a pure sinusoid xt as a function of time, and since this is a pure sinusoid, it has only one frequency, say f1 hertz. By using a tool called Fourier transform, we can actually convert this signal into frequency domain. So the horizontal axis becomes f, the vertical axis is now mod of capital X of f. Okay. So capital X is the frequency transform of small xt. By using Fourier transform, we can actually find what frequencies are present in this signal. So since in this case only a single frequency f1 of certain amplitude is present, we will notice that the Fourier transform of this signal will have a well-defined peak at signal f1. Ideally, mathematically, this would be an impulse function, but we'll not get into that. Let us just say there will be a very well-defined peak at f1. And the magnitude, the height of the peak will be proportional to the amplitude of this signal. So how exactly to find Fourier transform? These things we will leave for the next year when you take the course on signals and systems. There you will have to go through the detailed mathematical analysis of how this transformation is done. But for now, we will simply use the spectrum view option which is present in Folstat. Okay. So note that if this was a single sinusoid, this is how its frequency transform will look like, Fourier transform. If suppose there was another sinusoid of a much higher frequency, for instance, let's say f2 hertz. Okay. Let me call this as x1, so this is x1f. Let this be x2t. If I try to find Fourier transform of such a signal, I know that its Fourier transform will have a well-defined peak at some signal, some frequency, f2. Okay. If I added these two signals, for instance, what would I get? Adding two sinusoids will not give me a sinusoid, of course, because the frequencies were different, but it will still give me a periodic signal. So suppose the signal looks something like this. It is still a periodic signal. Let me call it x3t. Now, because Fourier transform is a linear transform, what we understand is that if we were to look at the Fourier transform of this compound signal, which is actually a sum of two individual frequencies, the Fourier transform of this third signal will simply appear as a summation of the Fourier transform of its individual components. Essentially, the Fourier transform will show us what all frequencies were present in this particular signal xt. This is how the tool of Fourier transform helps us find the frequency content of any signal. Note that by fundamental frequency, so when I say fundamental frequency, there will be some frequency content, the basic one, and then its harmonics, say 2f0, 3f0, and so on. So we are looking right now to identify fundamental frequency. Please understand that there is a difference between fundamental frequency and frequency content. What is that difference? If we go back and look at our old example, here f1 is the frequency content. Okay, coincidentally, because it is also a pure sinusoid, it is also the fundamental frequency of this signal. Same for f2. However, if you look at signal x3, you notice that this signal has component of f1 and f2 both. So fundamental frequency essentially would be to look at the periodic nature of this waveform. Suppose this is the time period of this compound signal. So the fundamental frequency of this signal will be 1 upon T naught. And ideally on the Fourier spectrum, you should see F naught and its harmonics if this was a musical signal. On Falstad, let us open a blank circuit, and here we'll go to draw. To bring in an input which is an audio signal, we will go to input and sources and connect an audio input. Okay, but before we actually connect an audio input, let me just show you how frequency spectrum is displayed. So just for an example, I'm going to take a simple one terminal AC source which is of 40 Hertz. Let me make this something like 400 Hertz. Okay, when you right click and view in a new scope, you can see this signal. To see its Fourier transform, right click within the scope, go to properties, within plots, select show spectrum. Okay, and you can see that it is showing me the spectrum and the voltage waveform superimposed on each other. Let me just uncheck show voltage and see how it looks like. So here you can see, because it was a pure sinusoid of 400 Hertz, you notice that if I take my pointer and place it accurately, it is about 400 Hertz which is showing. There are no other peaks which are visible. I am seeing just one single peak at 400 Hertz. Okay. To zoom in and out, you can use your scroll. Every time when you scroll in or out, note that the spectrum will have to readjust itself. So please give it some time to settle down. Don't immediately click on run or stop. So suppose I want to zoom in, that means on scroll, I will scroll down. You notice that my horizontal axis is expanding. Let me zoom out a little bit more. Okay. So what you see on the screen right now, let it have some time to settle down. And now if I view it clearly, I can see that this is almost 400 Hertz. Right? Note that this was a pure sinusoid, which is why I was able to view this. If this was not a pure sinusoid but an audio signal, rather recording of an audio signal, right, there would be many other noisy peaks around which we will ignore. Now to select a particular audio file, we are going to double click on this, choose file. I am selecting the C4 audio of a piano. Okay. So basically if you go to a virtual piano and these are all the keys, this particular key, this is C4. So I have recorded this audio and imported it here. Okay. So now this is also appearing like a voltage signal having a maximum voltage of 5 volt. So let us see how this waveform looks like. Right click, view in scope. Let me zoom out a little bit. So this is how the signal looks like. You can see it is clearly periodic. It has these peaks repeating after certain time. Let me zoom in and you can see how this signal is actually appearing periodic. Now we know that for a piano, the C4 key actually has a fundamental frequency of 261 Hertz. So to now actually view this signal, what we'll do is we'll go to right click, properties, within plots, we will show spectrum. Okay, and again like before, I'm unchecking the show voltage so that I can see the frequency spectrum clearly. By spectrum, we literally mean that the horizontal axis are various frequencies. So okay, let me reset it. Now I'm seeing multiple major peaks, but to identify those peaks, let me just adjust the horizontal scale. So I could scroll down and that will expand the scale, or I could have even gone to properties and adjusted the scale here. You can see how it is changing by looking at the bottom horizontal scale. So let me keep it at maybe 10 milliseconds per division. Okay, and I'm going to reset it, let it run. So some silent part of the signal would have come in the beginning. Now it is being processed. Okay, other peaks are going to settle down. I'm going to pause this waveform. Okay, you notice that the very first peak that I observe, that is my fundamental frequency, and that is rightly around 260 hertz. Okay, so I was expecting it to be around 260, 261 hertz. And you notice that the next major peak is at double the fundamental frequency. So if this was 260, this is around 520, and then 3 times, 4 times, and so on. Okay. So of course the size of the peaks will go up and down, because note that Fourier transform is actually calculated for a static signal. Okay, it should have finite number of samples. But what is happening in our case is we are actually running it through a audio file. So the signal is continuously changing, which is why the Fourier transform is also continuously changing. So at the beginning, if there was a pause, and at the end, if there is a pause, when the key is actually lifted, you will notice a change in the frequency. So that's why I stopped somewhere in the middle where the key was definitely pressed, and I'm looking at 4 major peaks rightly at the one that I expected, right? So this frequency is about 260 hertz. So the fundamental frequency of the C4 key in the piano is observed to be 260 hertz, which matches with the theory. We know this from childhood, that the human ear can hear from anything between 20 hertz to 20 kilohertz. Okay. But when we talk about speech, human speech, that frequency is not covering this entire region. Speech signals are actually typically less than 4 kilohertz. In fact, if you look at the fundamental frequency of the human voice, you will notice that is something between maybe 70 or 80 to 400 hertz. Okay. And you cannot, by just like listening to an audio signal, you cannot make out what is the frequency, fundamental frequency of the voice. However, if you were looking at just vowel sounds, like like somebody is saying only a, e, u, or for instance o, if you record somebody for a few seconds saying these vowel sounds, you will notice that those sounds will actually appear quite periodic, like how I just showed you in the previous case. Because they appear very periodic, you can clearly identify their fundamental frequency. And that becomes the fundamental frequency of the human, of the particular person whose voice it was, saying the sound in a particular note. Okay? So you will notice that male voices have relatively lower fundamental frequency, while female voices have a higher fundamental frequency. So in this part of the experiment, what I've tried is from some famous songs of Arijit Singh, I have identified and downloaded particularly sound bites for 2 vowel sounds, A and O. Okay, so the voice is of Arijit Singh, and what I would like you to do is play these audio files and watch the frequency content, and because these are vowel sounds, you should be able to view a very well defined fundamental frequency. Okay, so just for these 2 sounds, A and O. Now note that this frequency, what you observe, may change if some very high note is being made, like if E is being said at a very high pitch, this value will change, but the other 2 are kind of very base. So what I need you to find is, based on both these 2 single audio files, identify what is the fundamental frequency of Arijit Singh's voice at this particular note. To understand the next part of the exercise, we should know that although the speech will be less than about 4 kilohertz, which means if I took somebody's, so suppose take a recording of somebody singing without any musical instruments, and still the pitch goes up and down, normally the frequency content of such a signal, okay, should appear something like this. Okay, so a lot of it is focused on the lower frequencies, and gradually higher frequency content will start going down. If you have particular musical instruments playing, musical instruments have higher frequencies and their overtones as well, you will notice that this may then correspondingly change to, maybe something like this. It has more higher frequency content, but still if the audio is very loud, most of the content is focused on the lower end. Now the point is that this is a regular song, but suppose there is a audio where there is a sharp shrill sound somewhere in the background, like how sometimes when you're speaking in a microphone on the stage and there is a feedback suddenly, right, and there's a shrill sound uh, that comes. Okay? Suppose that is also recorded, right? Now that sound will have a very high frequency and it will be quite clearly differentiable from the rest of the signal. So ideally such a high pitch sound, suppose in this audio there is a high pitch sound, its Fourier transform will look something like this, which means you can clearly identify that this is that particular frequency which I want to identify, and the application here would be that once you identify it, you can actually pass it through a filter which just for this particular frequency multiplies the gain with 0. Okay, so something like this, the filter would look something like this. So here everywhere the gain is, say the gain magnitude is 1, and just here the gain magnitude is 0. So once you multiply these two, you just get rid of this particular frequency. Okay. So the whole idea of us trying to visualize frequency is so that in the next semester you are able to appreciate how by visualizing frequency or doing frequency analysis we can actually do filtering of signals. Okay, and we can de-noise certain signals. If noises are present, identifying those particular frequency and suppressing only those frequencies, how we can filter out certain noises. So in the third part, essentially I'll be giving you the first few seconds of a famous song which has a very well defined high pitch shrill. You need to identify what is the frequency of that shrill sound. Okay, on false start. Now the last part of this exercise is all about you playing an audio detective. To become an audio detective, you'll be using something which is called dual tone multi-frequency signaling, in short DTMF. If you look at your phone keypad, each of these keys is associated with a particular sound. So for example, when you press 1, this is how it sounds like. This is how 2 sounds like, right? So ignore these ABCDs for the time being. We are interested only in these 12 keys. Okay. You notice that each of these sounds are associated with 2 frequencies. So essentially, if you press 3 and you record this audio, when you look at the frequency spectrum of this audio, you should see 2 well-defined peaks, one at 697 Hz and 1477 Hz. Okay. Similarly, if it was pressing 1, if I record this audio and play it on false start and look at the frequency spectrum, I should see 2 well-defined peaks at these 2 frequencies. So the story is that you are monitoring some suspect, okay? You have wiretapped this person, but your warrant only covers the audio of the call. Okay, you do not really get by default the number whom this person was calling. Okay. So when you have the audio of this call, you also have the keypad recording. So using this keypad recording, and I'm telling you in advance that there is a 6-digit number which the person is dialing. Using this keypad recording, note that this is one single audio which is slightly long in length. So first key is played, then there is a pause, then second key will be played, third key will be played, like this. 6 keys will be played. So what you will need to do is this particular audio, which is already shared with you in that folder, you will upload this on Falstad and patiently let each of these keys pass. You can of course use the stop and run option on Falstad and look for each of these frequencies. What are the two frequencies it corresponds to? And you go back and look at that DTMF chart. So for example, you saw 770 and 1336. That means the key that was pressed was 5. Okay, so like this, complete this for all 6 digits and write the final identified number in the manual. So all this information is explained in the manual. The only thing you should be careful about is that in between these two keys, right, there will of course be some noise which is recorded. Okay? So don't get bothered by that noise. If the value of the signal is very low, like in millivolts, you can ignore that. A very well defined signal, you know by now that if it is actually a combination of two frequencies, it will look like a periodic signal, right? Like how I showed you the C4 key. Multiple frequencies are present actually in that key. So you know how that kind of a signal would look like. Please be careful not to worry about the noise that appears in between. We are not looking for that frequency content. Just focus on these digits. Thank you, and I hope you have fun.